Good morning, my name is Cynthia Cerón and I'm presenting the work in silico modulation of TRPV1 transmembrane cytoplasmatic and structural sites with the doctors Victorino Latriste, Liliana Martinez, and Alan Carrasco. As an introduction, the transient receptor potential cation channel, subfamily 5 member 1, is a channel permeable to cations, mainly to calcium, which is necessary for various processes such as cell proliferation and differentiation. TRPV1 is biologically active as a tetramer and is formed by an N and C terminal regions that are intracellular. The N terminal contains a region of ankyrin repeats with consensus sequence to modulate the activity of the receptor. The transmembrane region contains 6 domains between 5 and 6 is located in an aqueous pore to the entry of cations, mainly calcium. In order to study the functions of the TRPV1 receptor, capsaicin, an hydrophobic molecule and the main compound of chili peppers, has been used as a pharmacological tool. When capsaicin binds to the TRPV1 receptor, it produces pain and inflammation due to its presence in C and AD fibers, releasing peptides and other transmitters from the peripheral and central terminals. Different biological effects according to the dose of capsaicin has been reported. To high doses, denervation and cell death, and to low doses, release of neuropeptides and cell proliferation. Due to the different biological effects observed, the objective of this work is to identify the capsaicin binding sites in the TRPV1 receptor by an in silico molecular docking. The molecular docking was performed in Schrödinger using the next tools, protein preparation wizard, to optimize the protein. The crystallized structure was PDB7LR0, which corresponds to TRPV1 in tetrameric form. This structure is also co-crystallized with capsaicin. The structure was optimized by removing water residues from the molecule and assigning the corresponding chairs of the amino acid residues at a physiological pH. In leak prep, we charge the molecule capsaicin downlength from PubChem, and finally, in glide, we perform the molecular docking, looking for sites to capsaicin in transmembrane and intracellular zone. Our results found 9 capsaicin binding sites in TRPV1. In letter A, we have the top view of the receptor showing the transmembrane zone with 4 sites to capsaicin in pink circles. In letter B, this is the top view with a magnification showing the central sodium, which is a red particle, which has 1 site for capsaicin, and in letter C, we have the bottom view showing the intracellular zone of the receptor with 4 sites for capsaicin. The table of interaction energies shows that the transmembrane region with 4 sites has more negative binding energy. The negative the binding energy, the higher the affinity of capsaicin at the site. According to our results, the zone with the highest affinity in is the transmembrane zone. Now, in the next figures, we have the transmembrane sites found in the molecular docking. Amino acids are enclosed depending on the domain which they belong according to the color code. Capsaicin is a lipophilic molecule, so its affinity is for the transmembrane zone, rich in hydrophobic amino acids embedded in the cell membrane. For this reason, interactions with the aromatic ring of capsaicin are observed in the transmembrane zone. The site associated with sodium is a hydrophobic zone since it is in the cation pore. We can observe hydrophobic and polar amino acids. According to OTA and collaboration in 2008, sodium works as a plug that prevents the passage of the cations when the receptor is in its native state. So we propose that when capsaicin binds to the sodium site, it will cause structural changes, modifying the size of the cationic pore, allowing the flow of calcium into the cell. And finally, in the intracellular area, specifically in the ankyrin repeats, 4 capsaicin binding sites were formed. This with the lower affinity because this area is hydrophilic. The ankyrin repeats of the N-terminal domain have several binding sites for the proteins kinase, ATP, and calmodulin. This modulates receptor activity. The binding of capsaicin in this area will prevent the binding of the modulator, changing the functionality of the receptor. The fact of finding a large number of binding sites and in different areas will explain the different effects of capsaicin according to the dose, low-dose cell proliferation and high-dose cell death. In accordance with this result, we propose that at low doses, capsaicin binds in the transmembrane zone, activating the TRPV1 receptor, promoting a stimulating effect on the cell, and that by increasing the dose of capsaicin, the other sites begin to saturate in order to affinity. First the sodium site and then intracellular zone, activating different pathways in the TRPV1 receptor that will cause a different effect at a biological level such as cell death. Cell death occurs by an increase in the calcium current causing necrosis. So we propose that the increased entry of calcium is due to the moment in which capsaicin begins to occupy the sodium site, causing structural changes, modifying the size of the cationic pore, and that the binding of capsaicin in the ankyrin repeats will not allow the sensitization of the receptor. In conclusion, the TRPV1 receptor has 9 capsaicin binding sites at the transmembrane, structural, and associated with sodium and intracellular sites. This demonstrates the sensitivity by molecular interactions of the receptor according to the dose used. Thank you for watching, and there's my email, and you can comment if you have any thoughts.